Just turn it empty on slots. There you go. What's that?
That bottoms up thing.
Oh, the bottoms up.
Very cool.
It's quick. See, I'm the kind of person that got really bummed out when more and more change machines, automatic change, because that's the one place people get practice actually having to use numbers. So when they started changing, started coming out, I'm like,
But you got robbed less and less because people weren't messing it up.
yeah. Oh, I'm sorry, I'm bad with math. I'm sorry, I tripped you out of 20 bucks. No. That's a good point. All right, so chapter 2, I'm going to try to get up through 2-4, believe it or not, because the first 4 sections of 2 should be pretty quick. The last 3 sections of 2 are a little bit freakier, and they deal with some stuff that you might not have seen before. So I'm gonna hold off on those till Monday. But basically, who can remind me what a function is? What's like the math definition of function? I want to see this.
It's a result of
That's
it's a result of like a number.
So it's got to do with that idea. You plug a number in, you get a result.
Yeah.
But a little more specifically. So I always like to use this example. This isn't exactly what a function and why it is, but it's pretty close. If I ask somebody, what size shoe are you wearing right now on your left foot? And she tells me size 5 and 6. Do you have 2 shoes on there somehow? What the hell? I'm expecting one answer, right? So if I ask somebody, you throw a ball and you say, okay, 5 seconds later, where's the ball? And they say, it's 20 yards that way and it's 5 feet under the ground. What the hell happened there? Some kind of weird quantum mechanics thing. So the idea of a function, I always like to think of it as, if I know something's a function, I know it can model something in the real world. Now, there are things that aren't functions that could also model things in the real world, but I'm talking about very basic modeling. Like if I throw a ball, it's going to be a parabolic arc. It's not going to kind of cross on itself. That would indicate that it's in 2 places at once. You can argue that maybe Samurai came out of nowhere and chopped it in half, but then I call it 2 different things that I'm looking at, not the same thing that's in 2 different places. You guys kind of with me? So that's the basic idea of a function. That kind of leads into its definition. For every input, anybody ever watch Highlander? Remember Highlander?
Mm-hmm.
There was a show and they were at the movies and one of the movies was stupid and all kinds of stuff. So I'm really big into Highlander. I kind of like it. So the function definition is sort of like that. For every input, there can be only one output. So for all the Highlander fans, there you go. So for everything I put in, for every x value that I use, there can be only one output for each of those. So it's exactly the same as my input was on your left foot, and what size shoe are you wearing? Your output can't be 2 things. Your output can only be 1 thing unless you actually do have 2 shoes on there, right? You guys in this class should not be at a point where I have to get too detailed into any of this. If I wrote up here, and I said, what's f of -2, and what's g of, even if I did this, let me do this, what's g of f of, oh, you're going to get yourself in trouble, that's too bad. G of f of 3. Could you do those 2? Do them. some lame game show. Can you do that? Yes, do that. So what's that for negative 2? So I get negative 2 squared plus negative 2, 4 minus 2, 2. X is negative, so plus a negative. Be careful. To do this problem, what do you have to do first? Yeah, so it's just like anything. You start on the inside, you work your way out. So G of, I don't know yet. So G of, what's F of 3? 12. So G of 12, you get some nice numbers there. G of 12 would be 12 cubed plus 1 over square root of 12. I like it. 12 cubed is 1700 or something? Yes. 1720, so I get 1729. How do you reduce this? Yeah, square root of 4 is 2, square root of 3 leaves inside. And then you can rationalize and all kind of crap if you want to, but that's plenty far enough. And so that's the basics of function notation and how to do them and blah, blah, blah. Let me throw something a little more visual at you here. All right, so given that graph, what must f of 1 be? So let's see that way. F of 1 must be, this always trips people up when you first see it, if it's been a while. But if I give you a function, for example, this f, what point does it go through? Give me a point that it goes through.
1.
Negative
2 is not a point. Give me a point that it goes through.
Negative
1, 1.
Or 2.
It goes to the point negative 2, comma
2.
2. When the input is negative 2, x is negative 2, the output is 2. So how would I graph that? Wouldn't it go to negative 2 and then go up 2? So there, what's f of negative 2 visually? It must be 2 because that's where the hell the point is. All right, there you go. What's f of 1? Go to 1, where's the point?
1.
The output is 1 for an input of 1. You guys get that? Not a major deal, it's just a little click in your head. What's f of negative 2 in this case for this picture?
1.
1. Where is f equal to 3? For what input is f equal to 3? It's not 0. It's not f of 3. That would be 0. For what input is the output 3? 2. When x is 2, the output is 3. You guys see that? Okay, cool. So a graph, one reason we do graphs is it's the quickest way to show somebody all the answers. If you give me a function and I say, okay, write out all the answers, I'm like, okay, that'll take me the rest of everybody's life that will ever live and longer. So let me just give you a picture and you go find whatever the hell you want. All right? You guys with me? Some of you guys, this should be hopefully old news. So here's where we get a little bit funkier. One thing is, anybody know the volume of a cylinder? What's the base? What shape is the base?
Circle.
Circle. So the area of that base is going to be pi r squared. And how many of them are stacked up here is the height. So the volume would be pi r squared times h. Right? So the volume of that is pi r squared h. I would say that this is volume as a function of radius and height. You with me?
No.
No? This is volume. And the volume is dependent on what? Radius and height. Right? In fact, we'll think back. If I had that, this is f as a function of x. Right? F of x is a function of x. So I could even say, like, cost of x widgets is 3x squared minus 4x blah blah blah. This will be cost as a function of x, because that's what it depends on. This is volume as a function of radius and height. As the radius and height change, the volume will correspondingly change according to this. Is that better? So it's nothing major, it's just the way I've written it. Volume is a function of radius and height. Can you rewrite this so that height is a function of volume and radius? What's another way to say that? Just solve this for h, right? So if you make this h equal v over pi r squared, this is now height as a function of volume and radius. Is that a big deal? No. No. You just have to realize that's how you say it. So if you see something like that, hint, you know what they mean. It's really just saying good old algebra, solve for h or solve for r. They say, right, this is r is a function of volume and height, you solve for r. That's what that means. Maybe. So, for example, very often, and when I say very often, I'm thinking about calculus and I'm thinking about later in this class. You'll be given a function like this, and they'll also say, we've designed this thing so that the radius is always twice the height. So can you take this volume and make it only a function of height? How would you do that? What do you do? Everybody who shook their head, yes.
Plug 2h in for r.
Yeah, let's plug 2h in for r, right? Volume is a function of radius and height, but if radius itself is a function of height, then volume really is only a function of the one thing.
Height.
And you have done this before in word problems where you have the perimeter of this rectangle has to be 10, but the length has to be 4, so you just plug it in. You've done it before. You just never really said, I'm making this now a volume as a function of only height. You just never said that phrase. But now volume will be 2h squared is 4h squared, 4h cubed. Cool? Now volume is only a function of height. Now if you're interested, you actually write this, if you wanted to, you could write this as volume a function of radius and height. You're not going to see that too much in here, but that's how you could do it. Could you make, using this, could you make volume as a function of only radius? Probably because I wrote it up there. Instead of replacing r with 2h, you replace h with r over 2. You just replace the letter you don't want with something related to the letter you want, right? If you have it, and here we do. So we would plug into h, we plug r over 2. So you get 1/2 pi r cubed. So that would be volume as a function of radius. You with me? So, I mean, in real life, if you're doing an experiment, you might just change one input. You might change the amount of current you put into something. You might change the how many coils of wire I'm thinking about something I did in grad school. You might change the number of coils of wire you throw around something with the current going. You want a function that only deals with that thing you're doing. So you can see exactly what's going to happen with the end result. You with me? So that's why it's important to be able to do this, to have a single variable in your expression. Okay, maybe. Can you always do that? Of course not. The only reason we could do that right now is because I had a relationship between those two. If I didn't, I'm stuck with that. Of course. Okay. Hopeful. The big thing to get out of this is just that phrase about how to say, you know, volume is a function of radius and height, or height is a function of volume and radius, that kind of thing. And what that means, what it would look like. Now here's the second weird thing. Who's ever heard of a piecewise function? Whenever I hear this, I always think about Pennywise. Anybody ever seen it?
Yes.
They all flipped. But it's nothing that horrific. Well, it depends on your point of view, I guess. Maybe it is that horrific. Here's an example of a piecewise function. Oh yeah, you're already here. I got you. That's piecewise. And this is actually getting closer to real life. If I shoot a rocket off, there's an equation that models its motion. If I then turn on another booster, boom, that same equation is not true anymore for its motion. I've got to have some other equation kick in at some time. You with me? At some time, I kick it, some other thing comes into play. Now I've got to have some other thing modeling its motion. Now, an interesting question about this would be, is this a continuous function? I think I've thrown that word out a couple times before. Continuous? And continuous really just means you can draw it without picking your pen up. You might have heard that before. So continuous means it doesn't suddenly jump like that. You keep going. With me? And it doesn't have something like this. This would be an asymptote. Because I've got to pick my pen up to keep going. Okay. How do you think you could check? Is this by itself continuous? A line is continuous, right? And of course a parabola is continuous, that's fun. Any polynomial is going to be continuous. They're going to be nice, well behaved. What's the only place where this could have a problem? Where do things change? When is the function a line? When is the function a line? What do I say here? When the input is what? It is this when the input is less than or equal to 2. So it's going to look like a straight line for all the x's 2 and below. Right at 2, what happens? It's no longer this. What takes over? This. So something interesting happened there. It's just going along and all of a sudden kicking the afterburners and it goes crazy. So let's try to graph this thing. And people seem to think that this is going to be really difficult to graph. The only thing, you just draw a line like you normally would, you just stop at 2. You don't draw a line and then on top of that draw a parabola. That's not even a function anymore because it doesn't pass the what. If I do this, that's not a function. Now it's a here and it's here. Here and here. That's no good. So it doesn't pass the vertical line test anymore, right? So it can only be a line up to 2, and then the parabola takes over. So how the hell do you graph this thing? One way you can do it if you're haven't done this much before is to make XY tables specific to each situation. So you put in 2, you put in 1, you put in 0. What do you get at 2? Yeah, 6 minus 1, 5. 1? 2, 0, negative 1. And then it's just a line from there on out. That's great. So you don't, obviously you don't put anything over 2 because it's not allowed to have those inputs, right? So you can see why it's called piecewise. It's in pieces. If those pieces match at the borders, at the boundaries, then it might be continuous. So that's this guy. What about this guy? Here's what you want to do here. You will put a 2 in. Is it allowed to exist at 2? No, but I put a 2 in just to see where it wants to go, so I know where to put that open circle. So if I try to put a 2 in, what would I get? 5. That's not a point that I can graph. I'd have to put an open circle there. But what is here? At 2, this is, so this fills in that open circle. It would be continuous then. That line goes, and then the parabola takes over. Thank God my plane is not going, and all of a sudden, holy shit, how'd I get over here? Right, it's here, and then it takes over there. Then put a few more things in. 3, I get 10. 4, I get 17, blah, blah, blah. So to graph this thing, let's see what kind of scale do I want for this weirdness. All right. Let's see. That'll work. Okay, let's see how this works. So to graph the line, 2, 5, 1, 2. So 2, 5, 1, 2. And what was it? 0, negative 1. Cool. So that it's a line from here down. It's a line. Now I start graphing these points. 2, 5, cool. That's the open circle. Bam. Now it's not always going to line up, of course, right? I could have very easily put x squared plus 2. And this would have been 6, and there would have been an open circle up there. It would have somehow jumped. You with me? But this is a good example of a continuous piecewise. One fills in the other one. So you don't have to pick up your pen to draw it if you want to do the whole thing. 3, 10. Oh, where's 10? 10's right there. And then it would be 4, 17. So then it takes over as a parabola. Cool. Is that all right? So piecewise functions aren't that huge of a deal. You just are very careful at the boundary points, and you make sure that you draw the shape where it's supposed to exist. You don't overlap it. Then you have not a function anymore. It doesn't pass vertical line test. Okay, cool. Blah, blah, blah. Oh, cool. All right. I am certainly not going to worry too much about slope and y-intercept and all that kind of stuff. We should all know that mx plus b and all that kind of business. It's going to come up every now and again. But I do want to take a minute right now to look at the graphing calculator. So if you still need to borrow one, I got 5 left here. Yeah.
The anchored one that's on green, does that do exactly what the TI?
You know, that one I got to take off. I don't think it still works. The program, like right after I got it and put the link, they took it away, of course, because TI sued the dude and said, hey, stop. If he would have just made it not look like the TI calculator at all, I think they would have left it alone. Does it still work?
Yeah.
Okay. Because mine doesn't work on my Android anymore, but I haven't tried to download it. I think the minute it tries to update, it'll kill it. You know what I'm saying? So if you can stop it from updating at all, you'll be fine. So there is, if you don't know, on my website, there's for Android, so if you don't have Android, that's good. Even iPhone's got something amazing. There's an app for Android that mimics the TI-83. I think it's 83. And it's exactly like an 83. It's crazy. Like I just said, though, if it tries to update, they had a lawsuit, and that's why I put it up on the website, because they took it off the app market. But I think if it tries to update, it kills it. You actually have to own a TI and download the ROM into your computer, into your calculator, so that it will work. And then to your phone. You're like, what's the point then? So, but yeah, just try to cut it off from the outside world somehow, and then it'll be fun. Okay. What's that? Yeah. The only bad part about it is you can't use a phone on the test. But I will bring these with me. You just hopefully not too many people will need them. So you I desperately need more of you to get your own. Okay. My bag is empty. So let me do this here.
See, this would be good here. I might get enough of it.
And I want to show you one thing I added to the website. Anybody, I think one person was interested in the online homework, the Webassign. I'm pretty new to Webassign, but I finally, okay, good. So if anybody else is possibly interested, it'd be more money because you got to pay for access. But I put a link on the website here, how to sign up for Webassign. So if you want to look at it, go ahead. Yeah. Okay, here we go. How many of you guys have not used this at all? Really? Until? Okay, just a few of you guys. Okay. Can you turn out the whiteboard one? Yeah. All right, some basic graphing stuff. Let's all do this same thing. If you don't have a calculator, just watch intently. Obviously for graph, everything up here is for graphing. So y equals sounds like a good button to go to. Can you guys see this all right? I don't know. No? There's a chair right there. Let's all do something. Let's do something a little more interesting. Let's do 7x squared minus 9x. Why not? So this is going to come out looking like what? That's right, parabola. So if you do graph, oh, I get some neat stuff. I think this is my data from last semester for my stats class. So this is a good time to see if we have any freakiness in your calculator. Now if you hit graph and you see something weird like this, the first thing I do when I put a new function in very often is I'll do zoom 6 for zoom standard. It comes back to a -10 to 10, -10 to 10 standard screen, right? So you hit zoom 6, zoom standard. Now this one, there you go. This one comes out all right. Sweet. So we get a very narrow parabola, which you expect because it's 7x squared. The slope, all right, the 7 is huge, so it's going to be really narrow, really skinny. Cool. How are we doing so far?
What was the equation?
Oh, sorry. 7x squared minus 9x. Be real careful. There's a minus key and there's a negative key. Two separate ideas. If you try to put a negative there, it'll freak out. The nice thing is, real quick, if you do put a negative there and you hit graph, it goes, what does it do? Oh, it tried to multiply them. Neato. Because what's it going to look at this as? It's going to look at it as 7x squared times negative 9x. So that really sucks, you know. Let's just put the right minus sign in there. That's better. Now, what might be the most interesting point on that graph to look at? Vertex. And that's the turning point down there, right? So let me show you one cool little thing that I use a lot. Zoom box, the very first one under Zoom. So let me do that again. So go to zoom and number 1. You can either hit the number 1 or you can hit enter because it's on number 1. Now watch, if I move the cursor over a little bit and hit enter, it's going to be a corner of a box. And then if I move it down and over, it opens the box up. So it's pretty much like Google Maps. Going on a certain area. So I've opened my little box. If I hit enter, it's going to zoom in on that boxed area. Shlabang. So I can see that minimum a lot better. Okay. Where would you say this graph is decreasing? From what to what, roughly? Where is it decreasing? From negative infinity up to this vertex point, right? Whatever that is. And then it's increasing after that. So you're going to see in the book, in the homework, they're going to reference increasing and decreasing. They're going to give you a picture, and it's just that simple. Where's it increasing? Well, just look where it's going up. Answer in interval notation, right? From this to this, decreasing from this to this, so forth. Does anybody know how to find that point exactly? I could trace, if you hit the trace button right here. Exactly. If I trace, I get close, but it really bounces around a lot. So it looks to be close to like negative 2.89 something. And if I zoomed in even more, then I can make the trace even better. But I want the exact answer. So that's one thing I could do under this calc. Above trace, hit second, trace to get up to calc. So for those of you, I think most of yours should be in yellow, maybe, I don't know, your second key is in yellow. So it's like a shift key on a computer. I used to say typewriter there, and then it really, it's like, hey, try tape. So one thing we can do is minimum, and you're going to love this. It's going to ask you 3 questions. It's going to ask you, what is your name? No, it's going to ask you, what is your quest? No. It's going to say left bound, right bound, guess, because it wants to have, it's really interesting. There's a class a little bit further above this that you actually learn the algorithm it uses, and it uses calculus to try to figure out. It's called Newton's method. Oh, we don't need to know all that crap. Left bound. So what I normally tell my students, because left is a little weird, I say go right on it and hit left a few times, hit enter. Right bound. So go right back on the answer again, hit right a few times, enter. So see up here how it opens those triangles? So it tells you where it's going to be searching. And then it says give me a guess. So you try to get close to the answer, enter. So let me do that again. So now I got the exact minimum here. So you go to second, trace to calc, minimum, go to the left of it a little bit, go to the right of it a little bit, get right on top of it, bam. Okay. That's nifty. So let's do something a little niftier. Let's put in there a second equation on top of that. So hit y equals again. Put in here, what, Jeff? I don't know. 4x plus 4. Why not? So now when I hit graph, I'm going to be zoomed in kind of weird, so we might have to change that. Let's hit graph. Yeah, so there's my line. So what should I hit now to get back to kind of normal? Zoom 6. I love it. Zoom standard. So zoom 6. So there's my parabola, and there's my line. So what might I be interested in this situation? Like that's my laser. It's got a freaking laser. And there's the meteorite coming in towards Earth. So I want to know where will it hit the meteorite. So I want to see where they intersect. Yeah. And the one intersection is here, and the other one's off the screen. And this intersection is kind of messy, isn't it? So let me zoom box into that little area there. So I can kind of see this thing a little better. So there's a parabola. There's the line. Now I can see it nice. You guys kind of with me? So hopefully for some of you guys this is old news. You've done this a lot in your algebra. Maybe some of you guys had an algebra teacher that didn't really use the calculator very much, or at all sometimes, and that kind of sucks a little bit. You've got to get in and just start playing with it. There is homework problems even in chapter 1 that references you have to do it on the graphing calculator. It has a little graphing calculator feature next to the problem, right? So good places to get some practice. So how do you think I'm going to find that intersection? I could do trace again, but we already saw that kind of sucks. So where should I go to try to find this intersection? Yeah, go back into calc, second trace into calc, and we have exactly what we want. Number 5, intersect. Now, let me see if I can do this quickly. This kind of irks people, especially me right now. Here we go. So you got to kind of watch your, I want to be negative x. If you don't see it on the screen, you got to kind of watch your point so you know where the hell you are. If you hit the up and down button, it's just going to bounce between curves. If you just have one thing graphed, it's not going to do a damn thing. And I've seen people go, move, move. No, left and right move. Up and down bounce between equations. You with me? So it's going to ask 3 questions. It's going to say first curve, second curve, guess. The minute I say first curve, it bounces to the next curve in the list. And then when I say guess, I just go right to close to where they intersect and hit that. So the shortcut for finding the intersection is put the cursor right on top of the intersection, go to intersect, enter, enter, enter. Because you're already there, right? So to do that again real quick, I would just move it, it's already there. So I'd move it to the intersection, enter, 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 bam. So now I see where they meet. Meteorite exploded. Yay. Cool. How you guys doing?
Good.
Good. All right. So hopefully, like I said, some of you look very bored. I understand. If you've used this a lot in Math 110, you should have been doing exactly this. How do I see that other intersection? What's kind of a quick way to get up there? I just have to see up a little bit more, right? So where do I go to see up a little bit more?
Zoom out. Zoom out.
Zoom out sometimes steps way too far out. Go to window. And I just want to be able to see up a little more. So I want my Y max to be bigger. Let's just make it 20. So now I'm going to see on the Y axis, I'm going to see all the way up to 20. I should be able to see that intersect now. There it is. Cool. And then you can do the whole intersect, enter, enter, enter thing again to find that. All right. So how's that? I mean, I think just a few of you guys said you haven't used this at all, and I think a few more of you haven't used this much. Hopefully, most of you have done stuff like this before, because we're going to be getting a little bit deeper into this, obviously, this semester. If you haven't, you got to start playing around with it. Let's see. Something I desperately need you guys to know is the basic look of all graphs. So we all know what x squared stuff looks like. It looks like parabola. We all know, in fact, any even power on x squared, x4, x6, they're all going to look the same. They're just going to start getting skinnier because it's going to rise very quickly. Odd powers look like a parabola where half of it fell out, right? Because it's allowed to go negative, so it's not going to have to turn. It can actually just have its other part in the negative side. You with me? So I call it cubish. They look cubish. Because x cubed looks like this. What about a square root? Yeah, it looks like a parabola fell over and this half went away, right? So it's had a rough day. So parabola fell over, so it looks like you have a board, Jeff. You can draw. So square root looks like this. So just missing the other half of its parabola. What about 1 over x squared? So if I have a parabola as this, where would this have a problem? Where would something go freaky with this thing? At what point?
0.
Here's x squared, right? Yeah, at 0, this is going to be undefined. And the closer I get to 0 from either side, the bigger my outputs get, right? But the further I get from 0, what happens to my outputs for this? The further I get away from 0, like at -5, I'm at 25, this will be 1/25. So as I approach negative infinity or positive infinity, this should approach 0. It should keep getting smaller and smaller and smaller. So what this ends up looking like then is, it's kind of like this in reverse. It gets bigger here, so 1/, gets smaller, and then it goes to infinity at 0. And then the reverse happens here. Just like that. And the whole thing is above the x-axis. Why? Because it's squared. It can't be negative. So what would be different with, this is 1/x², what would be different with 1/x? The only true difference would be on the negative side, it actually can be negative, right? So it's going to look like that, that. So 1/x to an odd power would look like this. 1/x to an even power would look like the volcano over there, right? That's what I see. Let's see, anything else in namespace? What about absolute value? What letter of the alphabet does that look like? A V. A V, yeah. And you actually have an absolute value. You can graph absolute value here. If you go to math, num, the very first thing is absolute value. It's kind of nice. So you can do the absolute value of x minus 2. So the absolute value of x would be a v where the vertex part is at 0, right? Absolute value of x minus 2 is going to move somewhere. And one whole section in this chapter is about what's called transformations, where we take a graph and we move it around. So this is actually going to end up probably going the opposite direction of where you would guess. It goes up to. See, there's where the vertex is now. Let me zoom 6. All right, that's a little better. Cool. But the basic look of it is a V. And that's, now you see why I need you to know the basic look of these, because when we start moving them, you better know what they look like in the first place, and then you can just move them around. Not a big deal. Okay? Oh, I've already done that. Neat. We basically, this is nice. We basically already did section 2-3. You know, once you get into the idea of functions and graphs of functions, they're all kind of overlap. So I'll get ahead of myself sometimes. It's awesome. The only thing that really comes out of 2-3 we haven't talked directly about. Is if I have this graph of this monster strange polynomial. It's not as easy to find these as it is on a true parabola. A parabola has how many turning points? 1. Right? A cube can have at most 2 turning points, and so forth. So it's always, how many turning points could you possibly have at most? 1 less than the highest power. With me? Okay. So what power could this represent then? Here's a turning point, there's a turning point, there's a turning point, there's a turning point. Yeah, anywhere from x to the 5th up, but it has to be, could it be x to the 6th? What do you think? Because the end doesn't look like it's supposed to, right? If the x to the 6th, it should end up going like a parabola. It does weird shit in the middle, because then the really small values of x kind of take over in the middle. Maybe. Let's see what I want to say. So these are turning points. How many maximums does this? How many local maximums? Can you spell points? Yeah, there's what we call a local maximum. Why wouldn't I just call that a maximum? Because over here it goes to freaking infinity, right? So there's no like maximum here, but there's what we call local max and local min. Cool. So in the book, you're going to see things like, they're going to give you a picture, they're going to give you something like this, and it's going to say, identify the local maxes. So you'll say at the point 2, 3, there's a local max. The point, whatever the hell this is, 4, 2, whatever it is, there's a point, there's a local max. And then just to go back to something I said earlier, it's going to say, tell me where it's increasing, where it's decreasing. So for example, from here to here, from about -1 up to 2, it's increasing. You with me? Why would I make that a bracket? What's it doing right at -1? It's sitting there, isn't it? It's not going up or down, it's just sitting there. It's a turning point, so it's not doing it. So you officially wouldn't count those when you're telling me where it increases or decreases, because it's not doing anything there. Okay, cool. Maybe. Alright, cool. So I'll tell you what, let's see. Shouldn't take too long. I think we've done enough for today. What do you think?
Yes.
Plenty. So we've done officially 2.1 through 2.3. So when is that due? Yes. Next Wednesday is also the day of the review, because the Wednesday after that is the test. So we are going to try to finish up chapter 2. If we don't finish chapter 2 on Monday, that first test will just cover whatever we get up to. Cool.
It's due a week after it's done, but you don't have to turn it in until the day of the test.
Okay, I have a question.
So like it's due next Wednesday. And like Monday's over, it's due on Monday. But you're not kind of late unless it's after the test.
So we have a test on Monday, right?
No, on June 6th. Like 2 weeks.